Now let us do the reverse process. So what is that? So let us do the reverse process. So given impulse response of the system, how do you find the differential equation? Okay, so for an LTI system, this is reverse. Okay, so for an LTI system, impulse response, okay, so impulse response is given by h of t equal to e power minus 2t u of t. Okay, so impulse response is given by e power minus 2t u of t, let's say plus e power minus t u of t. Okay, okay, question is find, first question, find frequency response of the system. Okay, so find frequency again I'll write down h of j omega, we know that, right? So find h of j omega, and second one we will say find the corresponding LCCDE, linear constant coefficient differential equation. So this is a simple problem. So first one, so how do you solve the first one here? We want to find the frequency response of the system, which is nothing but Fourier transform of h of t, which is given by h of j omega equal to, what is the Fourier transform of e power minus 2t u of t? That will be 1 by 2 plus j omega plus Fourier transform of e power minus t u of t is 1 by 1 plus j omega. So this should be equal to how much? If you take the LCM and simplify, you will get 2 plus j omega multiplied with 1 plus j omega. What happens to the numerator? That should be 3 plus 2j omega. So this would be the frequency response of the system. So if you want to further simplify, we can write this as 3 plus 2j omega divided by, let us expand out the denominator. You get j omega whole square plus 3j omega plus 2. So that's easy to see, correct? If you multiply it out, you will get j omega whole square plus 3j omega plus 2. So finally, this would be our frequency response. Okay. So what is the second question? Second question is we have to find linear constant coefficient differential equation. So to do that, what is that we know? We know that y of j omega, right? Sorry, h of j omega can be written as y of j omega divided by x of j omega. So which should be equal to, as given, 3 plus 2j omega whole divided by j omega whole square plus 3j omega plus 2. Okay, so now let us do the cross multiplication. So doing cross multiplying, okay, so if you do cross multiplication, what do you get? So we will do like this. Okay, okay, if you do the cross multiplication, what you get? J omega whole square y of j omega plus 3j omega y of j omega plus 2y of j omega, that is the left hand side. So this should be equal to, that should be equal to 2j omega x of j omega plus 3x of j omega. Okay, so that would be the cross multiplied term. Now what we do, we take inverse Fourier transform. Okay, so taking inverse Fourier transform, which property we have to use here? Taking inverse Ctft. Which property we have to use? Again, differentiation in time domain. So which signal will have j omega whole square y of j omega? So we get d square y of t divided by dt square plus you will get 3 times dy of t by dt plus you will get 2y of t, which is equal to 2 times d by dt of x of t. Okay, plus 3x of t, correct? So right hand side also you have j omega x of j omega, means in time domain you have to differentiate once, and that is what we have written here. So 3x of j omega will have 3x of t as the corresponding signal. Okay, so this is the corresponding linear constant coefficient differential equation. So in that way, given differential equation, we can find the frequency response. Given we can find out frequency response and impulse response. So given, other way around is also correct. So given impulse response, you can find the frequency response, and from frequency response you can find the differential equation. So the corresponding frequency response will form the bridge between the impulse response and the differential equation. So in that way, this topic is very helpful. Okay, so with that we are done with our fourth chapter, which is continuous time Fourier transform. Okay, so we will summarize what we have seen in this chapter. Okay, so what is that we have seen here? We have summary of Ctft. Okay, so not summary of the topic, but it is summary of Ctft. So first we have seen definition. Okay, so definition of Ctft. Okay, then what did we see? Then we talked about existence of Ctft, correct? So existence of Ctft means what? We checked whether the signals at which signal will have the Fourier transform. There are two ways to do that. So what is that? One is to find what? You using Dirichlet conditions. Okay, so Dirichlet conditions, or there is another thing called alternative condition. So what is that? If energy of the signal is finite, still we can have the Fourier transform. Okay, and then we moved on to what are properties. Okay, so properties of Ctft, and how many of them were there? 13 properties we have seen elaborately. Okay, so many properties we have seen. Okay, so next we talked about what? Fourier Ctft of periodic signals. Okay, we talked about Ctft of periodic signals, correct? And then we talked about bandwidth of a signal, correct? Then we talked about bandwidth of a signal, and then we talked about what is the sixth one? We talked about sampling theorem, correct? So we talked about sampling theorem, and last we talked about LCCDE. Okay, last but not least, we talked about linear constant coefficient differential equation. Okay, actually we talked about indirectly which systems? LTA systems. So Fourier transform can be applied only to stable systems. So indirectly we can say that frequency analysis of any LTA system is done provided the system is stable. Okay, so and we have seen the simple examples from that. So given differential equation, how do you get impulse response? Given impulse response, how do you get the differential equation? And this happened through the frequency response of the system, and that's the reason why we have to bring in that LCCDE in Fourier transform chapter. Okay, right. So with that we are done with fourth chapter here. Next, let's move on. Let us solve a lot of problems and then move on to next chapter, which is Laplace transform. Okay.